Right, now we're at the United Kingdom Atomic Energy Authority. I'm going to find out about fusion, where now this is seen as, in so many different publications, in sometimes when the mass media bother to deal with these kind of issues as well, as the future and as indeed something that is going to allow us to hopefully start dealing with human-created climate change. So, where have we got to in terms of fusion? What is being looked for?
So it's going extremely well. We've recently broken the world record for the most fusion energy produced in a single stable fusion pulse. We have America and the National Ignition Facility who've recently gotten more energy out than they put in, so there's a lot of progress generally being made. We have recently bought a huge plot of land in North Nottinghamshire where we're hoping to build the first fusion energy power plant. So yeah, I'd say it's going pretty well.
And how is it created then? So let's understand. So
yeah.
From fusion, how is this energy created? And as you said, how to make energy beyond the energy that's going in?
Sure, so what we do is we take two kinds of hydrogen, deuterium and tritium, two flavors of hydrogen if you will, and we essentially heat them up super hot, 150 million degrees, and we hold them for as long as we can until they fuse together, they stick together, they make helium and a neutron and loads of fusion energy, and then that neutron goes flying off with all of that fusion energy. So a lot of what we're personally doing at the UK Atomic Energy Authority is figuring out the best way to do that so that we can eventually put it in a power plant. So what materials do we need? What maintenance facilities do we need? How are we going to catch that neutron because it goes just flying off? With the goal of making a fusion energy power plant.
Catch the neutron is, I presume that's on your t-shirts already.
Yeah, of
probably.
course.
So, what are the problems? What are the? Because this is.
We prefer the word challenges.
What are the challenges in terms of what is being faced at the moment?
So we have a few sort of key challenges at the moment. Material science is one of them. We have a huge materials research facility specifically for that. So I say that neutron goes flying off. Neutrons tend to go straight through whatever is in their path and bump into things along the way. So the question is, what materials can we develop that can withstand that? If we're going to build a commercially viable fusion power plant, what material does it need to be made out of? Because if we're replacing the whole thing every 10 years, that's not a commercially viable fusion power plant. So materials is a really big one for us. As I said, maintenance is another one. We're building a fusion power plant. We don't want to be sending human beings in, partly because it's very inconvenient to shut down a power plant. Again, commercially viable is the big thing. But also because it's not a nice environment for people to be in. There's going to be toxic chemicals in there, all kinds of stuff. So we're looking at remote handling, sending in basically remote-controlled robots to go and do work for us, creating stable plasmas that are high performance so that we can get more energy out than we put in. So I'd say those are some of the big ones. I think for a long time, a lot of fusion research was hypothetical. I mean, the joke that, it's always 20 years away, it's because people were wildly guessing, essentially. But now we have a plan going forward for maybe the first time, which is so exciting. You know, we've got the land in North Nottinghamshire where we're going to build STEP, the fusion power plant. Just the idea that there's a clear plan ahead and there's an exciting thing at the end of it.
And what are you doing? I can see the kind of Jenga blocks there.
They're mini Jenga blocks.
Mini Jenga blocks. So what are the mini Jenga blocks doing there?
So as I said, one of the things that we're looking into is remote maintenance, sending in remote-controlled, not supposed to call them robots, but robots, to do.
So why robots? Is that because now science fiction imagination means that we see the robots of a 1950s movie, or?
It's because robot kind of means something else. What we send in is a remote-controlled manipulator.
Right.
So
I think that sounds more threatening.
Yeah. Okay. I'm glad to hear that. So less a robot and more a thing you're controlling. So we have these little robots, little guys, and they are sort of a representation of the research we're doing into remote handling. And we have the Jenga blocks because our remote handling operators, who are very, very skilled and already go in and do maintenance for us, we make them play Jenga to demonstrate their skills. If you drop a screwdriver inside Jet, that's very, very bad. So we need them to demonstrate to us that they are top quality, and hence we make them play Jenga. It's a lot of fun using these guys. I would recommend it.
That's fantastic. Steve, I was just saying to you before we started filming, JWST has been an enormous problem doing the tour with Brian Cox, the Horizons tour, because it seemed that almost on a daily basis there was a cosmological image which usurped what was previously in the show. So just for you personally, what for you has been the most exciting, that bit which really you can feel the emotional kick in terms of cosmological images?
So I think there's got to be two. I mean, the images that are behind you right now of the Pillars of Creation, the real classics that first started off with Hubble. This is an image which I kind of grew up with. So I think the very first one was in the mid-90s when I was, still at school. And then I was lucky enough to work on the Pillars of Creation as viewed by Hubble when it was upgraded for the last time in 2009. And now we've got this whole new version, allowing us to see this great region of our own galaxy in exquisite detail. You're looking now through the dust to actually where these stars and planets are forming. So, those images are always going to be my favorites, but they're not the ones that I work on. So in a professional sense, they're not the ones that I care about. The ones that I care about are the deep fields. So these observations where we just stare for as long as possible at one empty patch of sky. And then when you do that, you see all these objects popping up. And these are galaxies stretching back across almost the entire history of our universe. So what me and my team do, we're all trying to find these very early galaxies, these first stars and first galaxies to form, and then we try and compare them with our computer models and see if we make sense of the universe. So whenever we see the new deep field or all these deep fields that we're getting, that's the most exciting for me. Even if they're not quite as beautiful as the Pillars of Creation, they are the ones that really, because I've been working on them for more than a decade with Hubble and now with JWST, trying to understand how the universe works.
I think JWST has given us a new lease of life. It's opened our eyes once again, even more than Hubble did. And just to see the clarity of these images that are coming back of the universe. And of course, the further we look into the universe, the further back in time we're going. So we're stretching back to that 13.8 billion years ago when the universe was created. And this is going to be able to educate us in ways we simply don't understand. And not only about the history of the universe, but also looking to the future, finding exoplanets, for example, being able to interrogate other planets and determine, perhaps they've got liquid water, perhaps they've got oxygen in the atmosphere. So there are so many things that James Webb is going to be giving us in the future. I'm really excited about it.
Now, I think for a lot of people there's an initial confusion. I think it's sometimes very hard to understand the idea of being able to look at early galaxies. So can you explain how is that possible?
So the key thing here is that light takes a certain amount of time to travel through our universe. So when you look at the moon, you're actually seeing the light that was reflected off the moon about a second ago. Now the moon's really close to us in kind of astronomical context, and so the further away we look in the universe, the further back in time we're really looking. So something like the Pillars of Creation, you're seeing it as it actually appeared a few thousand years ago, but that's really nothing either. The galaxies that I'm looking at, we're seeing them when the universe was only a tiny fraction of its current age, so we're having to look further away and therefore back in time. So when we make these deep field images, what you're seeing is, the universe changing and evolving over time, and our job as scientists is to look at those images, try and figure out how that is and why it's changing over time.
So if I apologise if I get this wrong, but we're talking billions, so it doesn't matter. But if the universe is, say, 13.7 billion years old, what age are we talking about? How far back are we looking at these galaxies?
Oh, so the most distant ones that we've now discovered with James Webb, maybe 300 million years after the Big Bang. So about 95% of the universe's history ago. So, we're getting there. We're getting to the point now where we're approaching what we call the dark ages. So we know at some point there wasn't any stars or galaxies in the universe, and we're now kind of observing the very first stars and generations to form. We can't look further with JWST, because beyond that there are no stars and galaxies. So we have almost reached this threshold. Not quite there yet. That'll take a bit more time to build up the observations, but we're really close to it. We're really close to finding the very first stars and galaxies.
So by looking at these ancient galaxies, how does that enhance our understanding of the universe and what it is?
So there's a whole load of physics that happens in the very early universe that we really don't understand very well. So how did the very first stars form? The reason why we don't know that is because they form from just hydrogen and helium. They don't form from the kind of mix of elements that we have today. So we're a little bit confused about how those very first stars form. The same is true of black holes as well. We know that our universe contains these supermassive black holes today, but we actually don't know for sure where they came from. And there are different ideas, but we know that they were being born in the very early universe. So by looking at galaxies in the early universe, we're hoping to answer, these two questions and others. How did the very first stars form? How did the first supermassive black holes form?
William, obviously when I was looking at the list of things in this pavilion, I was, fusion energy, quantum computing. Robot penguins is always going to stand out on that list. So we have 2 robot penguins behind us, emblazoned with the NHS logo. What is a robot penguin and what is it doing?
Story time. So we're a company that designs and builds self-driving cars. And so we got in touch, or actually co-contacted with an NHS trust who had a very specific problem which exists across the NHS called to take out. The problem simply goes, when you've been discharged from hospital and you now want to go away and all you're waiting for is your medicine, that wait could take up to 2 hours. But while you're waiting, somebody's not received their medicine. So the idea is now we simply automate the process of getting someone to receive their medicine when they've been checked out of hospital, and thus you get checked out sooner and there's less waiting times in hospitals. It's one of the biggest problems in the healthcare industry. So that is the use of the penguins. Now, you might ask why they're a penguin. Is when we embarked on this endeavor, we actually created a design competition. And we had over 100 designs of different sort of things from bots, and the NHS staff we worked with decided on a penguin. And thus Milton, the robot penguin, was born.
So it could be something that was made to look just very, very kind of bleak. And that's the thing that I think is really important scientifically generally when we look around here, which is to create something that starts with a story. Because when you start with a story, of the penguin and Milton the penguin, then you're beginning also that idea of the problems that the NHS are facing in terms of getting those medicines out there. That sticks.
For sure. I mean, humans are storytellers. So even consciousness is a story we tell ourselves to stay alive, right? It's a story. And so we try to wrap that in the most interesting, most fun way that's interactive, and you get it. And above all, it's simple. It's a penguin, but it's a robot. It's cool, right? Grabs people's attention. And so the story for us is how can we make life that little bit simpler? Not that crazy robot with arms and does it. No, it just solves one simple task there when needed and out of the way when not.
And what was your journey to getting involved in terms of this form of kind of engineering and design?
Actually, interestingly, I wanted to solve a problem in university, which was how do you find a book faster in the library? Because as a student, as a mature student, it took me 10-15 minutes. So why does this take so long? And so I invented the world's first robot librarian. Along with my co-students, we made this librarian prototype that would be able to find books by simply asking. And I remember on the very website where we were pitching this 7 years ago, I did say the future of this is healthcare robots. But the tech wasn't quite there yet. And I'm proud to say we're nearly there, and we'll soon literally be taking pre-orders for these things.
You're obviously a very ingenious person with a very, very curious mind. So I presume you have quite a long list of the problems that you would like to deal with in your career. So what else would you like to see? What are the ones at the moment that are most bubbling away?
Well, firstly, thank you for the compliment, because flattery gets you everywhere in life, so you can tell me more if you like. So I think in tech, we all, including me, try to solve the biggest problems felt by the highest number of people. And to me, this is a big problem felt by a lot of number of people. And for me, it's about the invisible problems. It's not the glamorous ones. We make self-driving cars, yes, but have you seen them? That's because our biggest customers are like the Defense Department. So everything we do is the invisible machines where they solve problems that no one else does really, because we're uniquely qualified to do so. So yes, I've got all sorts of crazy ideas, but the question I always ask is, how useful is it? Because the world really doesn't need a faster way to book a restaurant or a better dog walking app, which is what you'll get funded for $1 billion in Silicon Valley. So instead, no, I think stuff like this, when the problem is solved, then I stop, take a break and think, where is the world right now and what could be most useful next, that is not as glamorous, but actually solves a big problem, and it is big, but it's not really glamorous because no one else to do it, and we're uniquely qualified to do so. I think robotics should be fun. There's too much of that science fiction crazy story that it's going to end the world, but really it will if we make it so, or we take it that way. And for me, I'm just a guy who grew up in Africa, loved tech, and now I've learned modern witchcraft to make robots and robots' brains. And with that skill, I'll do my best to try push the world that tiny bit forward in a more positive way.
Here we are, IBM Quantum. The first thing, of course, people are now so used to hearing quantum ideas because they're all over every single film as generally as an excuse when they couldn't actually think of a plot point. They go, oh yes, something quantum universe. But the quantum computer, first of all, a definition of what is quantum computing.
So a quantum computer is a way of processing data using quantum mechanical effects. So it's a different approach to the way that a classical computer would process data. It uses some of these quantum mechanical effects in order to be able to solve problems that maybe wouldn't be solvable or be too expensive or take too long to solve on a classical computer.
So what is it that it can do that a classical computer can't? I mean, it's the number of calculations that can occur simultaneously?
No, what it does is it uses these three quantum mechanical effects of superposition, entanglement, interference, which introduces a level of parallelism in the way that it handles data and handles instructions, which means that certain problems like, for example, simulating nature. Nature is by definition a quantum mechanical system, and it's really very difficult to do that on a classical computer because you run out of oomph very, very quickly. You run out of bits, you run out of time, and there's growing evidence that a quantum computer will be able to address problems such as simulation, such as complex optimization, maybe even such as training data in machine learning better than a classical computer will be able to do.
So what would be a good example of a problem which would be quite impossible with a classical computer, but at the point of going, well, if a quantum computer is possible, these are the kind of questions that we can start moving towards an answer.
So a good example we use a lot when we talk to our potential clients is the example of a molecule of caffeine. So if you think one of the things that we believe quantum computers will be very effective for are things like drug discovery and new materials. And that's all about dealing with materials at the molecular level. So if you take a molecule of caffeine, we believe that to simulate a molecule of caffeine at rest, not doing anything, would take about 10 to the 48 bits. That's more bits than there are atoms in the world. We believe that it might take around 160 qubits. Now, logical qubits, perfect qubits, we don't have those yet. But what it does is it brings into the realms of possibility the ability to start simulating the way that molecules interact with each other. So that's a really good example where, while we don't have 160 logical qubits, which are perfect today, we are over that in terms of physical qubits, and our focus is on increasing the number and reducing the errors and things that we get with that to enable us to do that kind of job.
And you were, we were talking before we started filming, which is there are ideas which they work on paper, and many physicists will say, well, we know this must be true, but we don't have the engineering capability. So that's what you are dealing with. We've gone from the pencil and paper, and now you're dealing with the engineering problems of how to create a quantum computer. So, and we can see just behind, we'll get a shot of that, but we see the sense of what a quantum computer is. So what are the issues? What are the first problems that we face?
So the key fundamental problems, and we're trying to improve quantum computing in three areas. One is the number of qubits, and the number of qubits defines the size of the problem space that we can actually deal with. Crudely think about it as the number of variables that you can deal with in a problem. The second is the speed. You know, we call it the circuit layer operations per second. So circuit layer is like each step in solving a quantum problem. One of the challenges, particularly with the type of qubits that we use, is what's called coherence time. So it only maintains quantum state for a period of time when it collapses. And so how do we increase that coherence time so we can get more done? And the third thing is what we call the quantum volume, which is around the quality of the operations and the noise, and because noise interferes with the results. One of the challenges with quantum computers is that they're probabilistic. So unlike a classical computer, which is deterministic, you put in the same data and run the same instructions, you always get the same results. That's not true of a quantum computer. What you end up with is a probability distribution, and you use classical processing techniques to map that distribution into what the most probable answer is.
And what was, for anyone who's watching now, who's thinking this is a world that would intrigue me, and they're going through the education system, what was your journey in? What did you study at university, and when did quantum computing?
So interesting. So I'm a traditional computer scientist. I did a computer science degree at university. For quantum computation, it's maths. And I've talked at a number of school events, and people have said, you know, well, what good is maths in the real world? What good is statistics? What good is linear programming? It's all of those things. You know, actually, to turn a business problem into something that you can run on a quantum computer, it's about turning it into a mathematical model, and then turning that model into a quantum circuit that you can execute. So maths, statistics, probabilities, linear programming, linear algebra, these are all things that are really important if you're going to move into the quantum world. And you know, we are worldwide lacking in the skills that we need to actually really turn this into something that's going to drive businesses in the future.
And when you're watching films, as we said, the quantum seems to be almost omnipresent within science fiction, superhero movies, the wonderful Everything Everywhere All at Once. Are there certain things where you see quantum ideas being used so fast and loose that you go, I can't watch any more of this film?
Yes. You know, you'll see, I think Star Trek is a culprit. You know, my quantum tricorder. I you know, never say never, but you know, there are three things that we see quantum computation being very relevant to: simulation of nature and materials and stuff like that. Better machine learning, better training of machine learning models, better ways of optimizing really complex situations like, you know, pricing financial instruments or complex transportation networks or something like that. Outside of that space, it's difficult to see at the moment that quantum is going to have much impact. It will have very significant impact in those spaces. What it won't do is replace classical computers. It will work alongside them. You know, and if you think about the way in high-performance computing today, GPUs and CPUs work hand in hand. You know, our vision is that in the future, classical computers will work with GPUs and QPUs in the future, and QPUs will do the bits of a problem that quantum computers will be best at, GPUs will do the bits of a problem that a GPU is best at, and the classical CPUs will pull this all together. And it's sort of what we call quantum-centric supercomputing. It's sort of a mixture of all of these.
That's a great phrase, quantum-centric supercomputing. I'm going to use that more often. Really hope you enjoyed that, and we've got loads of other new ideas coming up. We've got quite a few things that we've made already, and we've got plans to make a lot more things. And if you can help, it would be great if you could go to patreon.com/Cosmic Shambles. And if you can't afford to, that's absolutely fine as well. But if you can subscribe, there'll probably be a subscribe thing there, or there, or there, or there. That would be fantastic as well.